Hello friends, in this video I am going to explain you the parameters of the operational amplifier. Let's see the outcomes of this video. The first outcome is input offset current and the second outcome is input bias current. Third outcome is input offset voltage and fourth one is differential input resistance. Fifth one is input capacitance and sixth one is supply voltage rejection ratio. Seventh one is common mode rejection ratio and eighth one is large signal voltage gain. Ninth one is output voltage swing and 10th one is output resistance. Let's see one by one. Here the first one is input offset current. Now first let's see what is input offset current. The definition of input offset current is the difference between the currents into inverting and non-inverting terminals of the balanced amplifier. If we take the balanced amplifier means the two inputs are connected to the supply. Okay, the two inputs are connected to the inverting and non-inverting terminals are connected to the inputs. Then the difference between those two terminals, the current difference between those two terminals is known as input offset current. That is IO naught equal to within the modulus IB1 minus IB2, where IB1 is the current flowing through the inverting terminal and IB2 is the current flowing through the non-inverting terminal, is equal to 200 nanoamperes. This 200 nanoamperes per 741 IC. Okay, if we consider 741 IC, then the input offset current for 741 IC is 200 nanoamperes. Now coming to input bias current. Okay, the average of the current entering the input terminals of the balanced amplifier. Here in input offset current we take the difference between the currents two input currents, but in input bias current the input bias current is defined as the average between the two input currents. First one is IB1. Here IB1 is the first input current and IB2 is the second input current. Now we need to find the average, that is by 2. This is the input bias current. Okay, this is the input bias current. Let's see here the input bias current IB is equal to IB1 plus IB2 by 2 is approximately equal to 500 nanoamperes. Okay, 500 nanoamperes. This is about input offset current and input bias current. Now let's see input offset voltage. What is input offset voltage? Let's see here the differential input voltage that exists between the two input terminals of the op amp without inputs applied. We can define the input offset voltage as, let's see here, this diagram. Here there is no input is applied to inverting and non-inverting terminals, those are simply grounded. Now the difference between these two input terminals, first one is non-inverting and second one is inverting terminals, then that difference is known as input offset voltage. Okay, let's see here voltage is V1 and here voltage is V2, and the difference between the V1 and V2, that is V1 minus V2, is nothing but input offset voltage. That is when these two terminals, that means the two input terminals are grounded, then only the difference between the two input terminals is known as input offset voltage. We can also define the offset voltage as the voltage that must be applied between the input terminals of an op amp to the null output. That means if I apply some input voltage, like here observe, here I applied Vi naught is the input voltage, but the output, here consider the output is the 0. Whenever the input is applied to the op amp but the output is 0, then that input also known as input offset voltage. Okay, here we have two definitions for input offset voltage. First one is without any applied input to the op amp, the difference between the two input terminals is known as input offset voltage, and the second definition is with the applied voltage to the two inputs of the op amp, when the output is 0, then that input is known as input offset voltage. Next let's see differential input resistance. What is differential input resistance? The equivalent resistance that can be measured at either the inverting or non-inverting input terminal with other terminal is grounded. Differential input resistance is nothing but measure the input resistance between the, or measure the input resistance at inverting or non-inverting terminal when the other terminal is grounded. We can measure either inverting or non-inverting terminal, but the other one is must be grounded. Then that input resistance is known as differential input resistance. Normally the differential input resistance Ri equal to 2 mega ohms. Now coming to input capacitance, let's see the definition of input capacitance. The equivalent capacitance that can be measured at either the inverting or non-inverting terminal with respect to ground. Here also the same thing as like differential input resistance. The equivalent capacitance that can be measured at either inverting or non-inverting terminal with respect to ground. Okay. Here we can measure the capacitance at inverting or non-inverting terminal also, but the remaining terminal what is left that must be grounded. Okay. Here the input capacitance Ca is equal to 1.4 picofarads. Now let's see supply voltage rejection ratio. It is also called as power supply rejection ratio. Supply voltage rejection ratio is also known as power supply rejection ratio. Let's see the definition of power supply rejection ratio. The ratio of change in the input offset voltage to the corresponding change in the power supply voltages. It is simply called as the ratio of input offset voltage to the power supply voltages. Here SVRR. SVRR means supply voltage rejection ratio is also known as power supply rejection ratio, that is PSRR equal to del Vi naught by del V. Here del Vi naught means change in input offset voltage by del V means what is del V? The change in power supply. It is approximately equal to 150 microvolts per volts. Now coming to common mode rejection ratio. Common mode rejection ratio is very important. The definition for common mode rejection ratio is the ratio of the differential voltage gain AD to the common mode voltage gain. We know for op amp we have two types of modes. First one is differential mode, another one is common mode. We know the differential mode the gain is AD. For differential mode the gain is AD, and for common mode the gain is ACM. The ratio of differential mode gain by common mode gain is nothing but common mode rejection ratio. Here observe CMRR equal to AD by ACM equal to 90 dB. Okay, where AD is nothing but differential mode gain, that is the differential output voltage by differential input voltage, that is VOD by VID, and the common mode input voltage common mode gain, that is ACM is equal to common mode output by common mode input, that is V naught Cm by Vcm. Okay, the common mode rejection ratio is also defined as the ability of the differential amplifier to reject the common mode signal. Okay, it can also defined as how much ability to have the differential amplifier to reject the common mode signal. That is nothing but common mode rejection ratio, and higher the CMRR better the rejection, which means if we have the high common mode rejection ratio, then it is having the ability to reject the common mode signal is more. Okay, now let's see large signal voltage gain. Large signal voltage gain is also known as normally voltage gain. We know voltage gain is nothing but the ratio of output to the input. Here itself written the same thing. The ratio of output voltage to the differential input is nothing but large signal voltage gain or simply voltage gain. That is A is equal to output voltage by input voltage. It is approximately equal to 2 lakhs. For op amp, we know for op amp the gain is very high, that is approximately equal to the 2 lakhs. Now coming to output voltage swing. Output voltage swing, that is the maximum unclipped peak to peak output voltage that an op amp can produce. Output voltage swing is nothing but the maximum unclipped peak to peak output voltage that the op amp can produce. That is nothing but the output voltage swing. Now coming to output resistance. In the previous slide we already discussed about input resistance. Now coming to output resistance, that is the equivalent resistance that can be measured between the output terminal of the op amp and the ground. It is also defined as output resistance, and this is as the equivalent resistance that can be measured between the output terminal of the op amp and the ground. It is measured between the output terminal and the ground. That resistance is known as output resistance, and it is approximately equal to 75 ohms. 75 ohms. Now coming to output short circuit current. What is output short circuit current? The short circuit current withstanding capability of the op amp. Okay, the withstanding capability of op amp for short circuit current is known as output short circuit current, and it is denoted as ISC equal to 25 milliamperes. Okay, now let's see what is supply current. We know supply current is nothing but the current which is supplied to the op amp for operating. Here the current drawn by the op amp for the from the supply. How much current drawn by the op amp from the supply is known as supply current, and the supply current is denoted as IS. Here IS equal to 2.8 milliamperes. Now coming to power consumption. Power consumption is nothing but how much power an op amp utilizes for operating is known as power consumption. Let's see here, amount of quiescent power that must be consumed by the op amp in order to operate properly. How much power it consumes in order to operate is known as power consumption. In generally, power consumption PG is equal to 85 milliwatts. Okay, and the coming to last parameter of the op amp, that is gain bandwidth product. Gain bandwidth product is defined as the bandwidth of the op amp when the open loop gain is reduced to 1. That is, in generally, gain bandwidth product is equal to 1 megahertz. Gain bandwidth product is nothing but the bandwidth of the op amp when the open loop gain is 1. Okay, that is known as gain bandwidth product. I hope you understood this topic. Thank you for watching this video.